So now this is the, so instead of visualizing the circuit in this way, it is easy if I am visualizing in this way. So at the input side, you see R1 and R2 are parallel. At the output side, you see R1 and R2 are series. And your emitter is grounded because both are common emitter amplifier. Input is Vs. Output I take from the collector of the second transistor. And the gain of first amplifier is AV1. The gain of second amplifier is AV2. And total output voltage is taken across the second amplifier, and VF is taken across R1. So if you apply voltage division technique, VF equal to total voltage V0 into R1 by R1 plus R2. It is voltage division technique. So you know beta is VF by V0, rearrange and cross multiply, you will get this beautiful expression, beta equal to VF by V0 equal to R1 by R1 plus R2. So the value of beta is not 1 here as it was in the previous case for emitter follower and source follower. Beta value is a fraction here. Beta equal to R1 by R1 plus R2, and beta value is always less than 1 here. Because you can, the reason is known, R1 by R1 plus R2. I'm dividing R1 by a value more than R1. So beta value is going to be less than 1 for this type of voltage series feedback pair. So this is the practical circuit of a voltage series feedback pair with all the coupling capacitors. See how to remember the circuit. I will say you just follow the lecture very carefully. Draw the first transistor, R1 biasing resistors, collector resistance, emitter resistance, bypass capacitance. Then so again draw one more transistor, voltage divider bias, collector resistance, emitter resistance, bypass capacitance. So I have drawn two identical common emitter amplifier. From take the output of first transistor and couple it through a capacitor and give it to the input of second transistor. And add a coupling capacitor at the input, add a coupling capacitor at the output. From the output of second transistor, connect R2 and that should go and join with R1 at the emitter of the first transistor. So this is going to be R1. So this R1, R2 follows the feedback combination. The circuit shows the two-stage common emitter amplifier with voltage series feedback by connecting the second transistor collector to the first transistor emitter through the resistance R1 and R2. So I am connecting the output from the collector of second transistor to the emitter of first transistor using the combination R1, R2 voltage divider transistors. Okay, I am using these two resistors to ensure that I connect them in such a way that a voltage series feedback connection is happening. Okay, see this amplifier we are not going to analyze in depth because already for one transistor if you apply H parameter equivalent circuit it is becoming very big. Now you see you have two transistors in cascade, so it is going to be very big and it is not going to be that easy. So we'll directly see how a problem is solved for voltage series feedback pair. So we can see the AVF will be approximately equal to 1 by beta, and this will ensure that the transistor will be stabilized for variation in temperature and other parameters. So even if temperature is going to change, this negative feedback will ensure that the temperature change is not going to affect the performance of your amplifier. Okay, so for this voltage series feedback pair alone, the analysis is not there in the syllabus because I told you it is going to get complex. But for the previous two cases, common collector and common drain amplifier, we did analysis using the low frequency model for FET and H parameter equivalent circuit for BJT. So that was done because it was a single configuration or single transistor. But since here you have an voltage series feedback pair, you have two transistors, analysis can be done, but since it is going to be complex and time consuming, we are going to directly